Okay, and for this last video, in sections 13.8 and 13.9, we're going to look at question number 7. It says, use Lagrange multipliers to find the max and min values of f when they exist, subject to the given constraints. So this is just like question 6, but the main difference here is that our functions are now of 3 variables as opposed to 2 variables. So looking at part A, okay, we have our objective function f of x, y, z, that's 2x plus z squared, subject to the constraint x squared plus y squared plus 2z squared is equal to 25. And I'll go ahead and write that in the form g of x, y, z is 25, where g of x, y, z is x squared plus y squared plus 2z squared. All right, cool. So we're going to proceed in just the same way that we solved the questions in problem number 6. We're going to start by finding the gradients of f and g, so those are here. And then I'm looking for the points x, y, z to satisfy these two equations, right? So I need the gradient of f to equal lambda times the gradient of g, and I need the point x, y, z to satisfy the constraint equation. Okay, so starting with equation 1 here, I set the gradient of f in blue equal to lambda times the gradient of g in orange. And now I'm going to go ahead and equate I components, so 2 is equal to 2 lambda x. J components, so 0 is 2 lambda y. And k components, 2z is equal to 4 lambda z. Okay, so this first equation, just dividing both sides by 2, can be written as lambda x is equal to 1. Okay, the second equation, that's lambda y is 0. And then this third equation I can rewrite as quantity 2 lambda minus 1 times z is equal to 0. Okay, one thing to point out here, since lambda times x is equal to 1, lambda cannot be 0. Okay, and if lambda cannot be 0, and I know that lambda times y is 0, dividing both sides of this equation by lambda implies that y has to be 0. All right, that's nice. Okay, next we can look at this third equation and consider the case where this first factor, 2 lambda minus 1, is 0. Okay, I'll call this case 1. So here, lambda is a half. Now, if lambda is a half, if I go back to the first equation, lambda x is equal to 1, that implies that x has to be 2. Now, go to the constraint equation, right? I know x is 2, I know y is 0, so that allows me to solve for z, right? I get that 2z squared is equal to 21, right? Because I'm squaring the x there, and that gives me a 4, and I subtract that over. Now I can go ahead and divide by 2 and take square roots. I get that z is equal to plus or minus the root of 21 halves. So this gives me these 2 points, 2, 0, root 21 halves, and 2, 0, negative root 21 halves. Okay, cool. So now, let's look at this second case here, right? That's where the factor z is 0. Now, if I know that z is 0 and y is 0, again from over here, I can find x by just going to the constraint equation, right? So if I set both y and z to 0 in the constraint equation, I get that x has to be plus or minus 5, so that gives me these 2 points. All right, cool. So now let's go ahead and find the corresponding function values at these points. So plug them into this objective function. If you plug in plus or minus 5, 0, 0, you get the corresponding outputs plus or minus 10. Plug these other points in, okay, you wind up getting 29 halves. All right, so as far as our minimum value, well, that's going to happen when the output is negative 10. And the largest value from this list is 29 halves. Notice 10 is not a max or a min, right? Because, well, again, I'm looking for the largest output value from this list and the smallest output value from this list. So that'd be negative 10 for the smallest and 29 halves for the largest. Okay, great. So that's part A. Let's then turn to part B. Pretty similar. So for part B, Okay, our objective function is f of x, y, z is equal to x times y times z. And here we're subject to the constraint x squared plus 2y squared plus 4z squared is equal to 9. So I'll write that as g of x, y, z is equal to 9, where here g of x, y, z is x squared plus 2y squared plus 4z squared. All right, so just proceed just as we did part A, right? We have the gradients of f and g here and here. We're looking for the points x, y, z that satisfy these two equations. Gradient of f is lambda times the gradient of g, and we need to satisfy the constraint equation. So going from equation 1, right, setting the gradient of f in blue equal to lambda times the gradient of g in orange, I can equate I components, so yz is equal to 2 lambda x, j components, so xz is equal to 4 lambda y, and k components, so xy is equal to 8 lambda z. All right, so now I'm going to do something that I did, at least it was sort of similar to something I did back in question 6, part B. Notice here in these equations I have a 2 lambda x, a 4 lambda y, and an 8 lambda z. And then on the left side I have a yz, an xz, and a xy. Okay, so I'd like to try to come up with some common expression across these various expressions I see in the equations. And I can come up with one as follows, right? Here for the yz, I'm missing this factor of x. Here for this xz, I'm missing a factor of y. And here for this xy, I'm missing this factor of z. So I can, in other words, multiply both sides of this first equation by x. That's going to give me an xyz. And over on the right, I'm going to get a 2 lambda x squared. From the second equation, multiplying both sides by y, that also gives me an xyz. And then that has to be equal to 4 lambda y squared. And then for the third equation, multiplying both sides by z, I get, again, xyz. That's got to equal 8 lambda z squared. All right, so now I get that these three expressions are equal. All right, so we're going to look at the following case, right? If lambda is 0, okay, well then 2 lambda x squared, 4 lambda y squared, and 8 lambda y squared, those are all equal to 0. So that implies that x times y times z is equal to 0. But that tells us, right, that f, because remember, f is just x times y times z, that must equal 0. So if lambda there, the Lagrange multiplier, is 0, the corresponding output value for f would have to be 0. Okay, so then let's now consider the case when lambda is not 0. So I'm going to look at these three expressions, right? I know they're equal. I can go ahead and divide through by 2 lambda. And since lambda is not 0 here, that's an okay move to make. So I get that x squared is equal to 2y squared is equal to 4z squared. All right, so now let's go to the constraint equation. Okay, so notice here, right, I have x squared plus 2y squared plus 4z squared is equal to 9. But what do I know about 2y squared? It's equal to x squared. And what do I know about 4z squared? It's also equal to x squared. So this left-hand side of the constraint equation is actually x squared plus x squared plus x squared. So I really have 3x squared is equal to 9. Solve for x, you get plus or minus root 3. Now I can go ahead and find y. How? Well, use the fact that x squared and 2y squared are the same. And since x is plus or minus root 3, that implies y is plus or minus root 3 over 2. Okay, and then lastly, to find z, use the fact that x squared and 4z squared are the same. So z is plus or minus the square root of 3 divided by 2. Okay, so now go ahead and look at the corresponding function values at these corresponding points. And I'm just going to multiply the x, the y, and the z coordinates together, and that gives us plus or minus 3 halves times the square root of 3 halves. And so, right, since I just have these two possible output values, we have our max is positive 3 halves times the root of 3 halves, and the min is negative 3 halves times the root of 3 halves. And that does it. All right, great. Thanks so much. I'll see you next time.